All right, tonight we're going to be talking about the basics about the periodic table. But in order to know this, you're going to need to understand how the periodic table was actually developed. It wasn't discovered. It's not like there was this sheet magically with the periodic table of elements discovered, but it was actually, how was it organized? How was it developed? And by 1700, there was only 13 elements known, which is actually kind of amazing when you think about the lack of technology that existed back then. There was no electricity, and yet they knew that 13 different elements existed. Yet by the mid-1800s, so in a century and a half, they had discovered over 70 elements. And why? The reason why this great increase occurred was because they started to use the scientific method. And what that allowed were, it allowed the chemists to talk to one another, and it allowed a systematic process where you could base your studies off of other scientists' studies. And so you could discover things at a faster rate. Now, because we had over 70 elements, we needed to start to organize them. And first what they did is they based it entirely off of their properties. And it was based off of their chemical reactivities and their chemical properties, because that's what they were studying. That's what they focused all of their attention on during this time. And what they came up with were these things called triads. And triads were groups of 3 elements, so they would partner all these elements up or group them all up that had similar properties. So an example would be chlorine, bromine, and iodine. And even though they looked very different, they had very similar chemical properties. For example, they all reacted with metals, so they would be grouped in this triad, which is 3 elements. Well, with over 70 elements, a triad still becomes very confusing because you're talking over 20 different triads. So along came Mendeleev, and Mendeleev was obsessed with trying to figure out an even better pattern than putting them into groups of 3. And he was a Russian chemist and teacher, and he devoted his a lot of his time to try to sort these. And what he did is he put the chemical reactivities, the masses, any characteristics that he knew about these elements, he put them on note cards and he tried to sort them to figure out the best method to develop this table. And what he ended up with was actually the first periodic table. And how did he sort it? He figured that the atomic mass was actually the most important, not the reactivity, but the mass. What was so impressive about his was that for 2 reasons. One, he left blanks in his periodic table for unknown or undiscovered elements. At the time, he believed that there were spaces in his, not because that there were meant to be spaces, but because there were actually undiscovered elements that were supposed to fill those spaces. The other thing is that he believed that some of the accepted atomic masses for given elements were actually wrong. And so that was an amazing thing to actually question the scientists of the day. But his periodic table was not without flaws, and I'm going to focus on argon and potassium, even though all of these other guys actually have the same fault. Argon has a greater atomic mass than potassium. So according to Mendeleev's periodic table, argon should go after potassium. But according to chemical properties, argon should go before potassium due to what it reacts with and so on and so forth. So his was not flawless. And what I'm going to show you is here's a picture of Mendeleev as he's working at an older age. And this is an example of his periodic table. And the 2 things I want you to note is first the question marks with an atomic mass written after it. And those were his undiscovered elements. So he believed that after zinc, which they knew about, and before AS or arsenic, that there were actually 2 elements according to his periodic trends that they hadn't discovered. Then the other one that I want you to focus on is like gold, for example, or Au. Au has an atomic mass, according to back then, a different atomic mass than what he believed. He believed that its atomic mass should be 197 or approximately, but that was not the accepted atomic mass at the time. So instead, he wrote it with a question mark after it. So those were the 2 reasons why his periodic table was so amazing. Number 1, he filled in space, or he left blanks for ones that he felt were undiscovered, and 2, he actually questioned the accepted science of the time. So because Mendeleev's had some faults, along came Henry Moseley, and he tried to improve upon Mendeleev's periodic table. And what he decided is that a better alternative would be if you base it off of atomic number, or as we've already learned, this is the number of protons. And this is what we're actually using today, because it fixed all the flaws that Mendeleev actually had in his. So what you need to know is that Henry Moseley developed his based off atomic number. It is the one that is currently used today, and the Mendeleev used his based off of atomic mass. All right, so there are different parts about the periodic table that you're going to need to become familiar with different terminology. The first one is periods. Instead of calling rows of the periodic table, we call them periods. And how I always remember that it's a period is it's a period of time is written horizontally. So how do we write a period? It's the one that goes in a row. It's the one that's horizontal. The more important one, though, that we will be talking about are groups or families. And groups or families are the columns. And what's so cool about groups or families, if you look at the word groups or families, is that a group or family has a similar characteristic. So, for example, if you're a part of the Environmental Action Club, you guys are a group. And why? Because you care about the environment. So you have some sort of similar characteristic. Well, groups or families are the same, and the columns of the periodic table have very similar chemical and physical properties, which is actually surprising because when you look at a column, they are farther from each other by number than period. So a lot of people would assume that people or the elements that were in the same period would have similar properties, but that's not the case. It's actually the ones that are in the columns that have further numbers from each other that have similar characteristics. And you do absolutely need to know that groups or families or columns have very similar characteristics. And the whole reason why is because of these things that we'll talk about, which are valence electrons. Okay, so they all have the same number of valence electrons as a group or a family. All right, so here's just a pictorial of periods. So periods are, once again, rows. Groups or families are columns. And some of these groups or families actually have special names to them, which we will be learning about in another video. All right, so let's focus on these valence electrons and why are they so important. First off, let's talk about their location. Valence electrons are the ones, if you looked at an atom, the center dot is going to be the nucleus, and these are going to be the orbits or the energy levels that the electrons exist on. So right now, the first energy level can only have 2 electrons. And if it has 2, it is called a duet, which makes sense because a duet has 2 people. Then if we look at the second energy level and every energy level after that, it can hold up to 8 valence electrons. So we've got 1, 2, 3, 4, 5, 6, 8. Okay, so it can hold up to 8, a max of 8. After it has 8, then you would have to add another energy level, and that too can hold up to 8. All right, but looking at this, the valence electrons are the ones in the outermost energy level. So in this particular case, this one has 3 electrons in its outermost energy level. So that means it would have 3 valence electrons. Okay, you kind of ignore these ones in the inside energy levels. Why? Because the ones on the outside are the ones that dictate everything. They're the ones that are gained or lost during a chemical reaction. They're the ones that are shared. They're the ones that are involved in absolutely everything. Because of their location being on the outermost, they are the ones that are easily lost, gained, touched, whatever. The ones on the inner energy levels, like these guys, these groups right here, those are really hard to get to. So basically, we don't care about them as chemists because they're the ones that aren't involved in any of the chemical reactions or anything. So as chemists, basically all we care about are the valence electrons. You need to know that the only ones we really basically care about are valence electrons. Okay, because they dictate everything. Now, how do they dictate it? Well, let's first count how valence electrons are counted. All right, so I've already drawn one over there. Let's do another one just as another example. So this is the nucleus, we're going to pretend, and here's 1, 2, 3, 4, 5, 6. So this element has 6 electrons total. And I'm going to assume it's neutral, so that means it would have 6 protons, which means that we are talking about carbon. But as far as valence electrons, are the ones that are in the outermost energy level, or the ones that are involved in bonding, it would have 1, 2, 3, 4. So carbon actually has 4 valence electrons. All right, now what I want you guys to do is take out your periodic table, and above it, I'm going to want you to write VE, or for valence electrons, and then I want you to write the numbers above each column. So under the first column or above it, write 1, above the second one, write 2, the third one, write 3, 4, 5, 6, 7. The last column's a little different because of that first energy level only having 2. That helium one can only have 2 valence electrons, but everybody else in that group can hold up to 8 valence electrons. So you are going to need to understand by just looking at the periodic table how many valence electrons an element has. So all you have to do is count the columns. For this class, we don't need to worry about these groups or these areas. All you need to do is count the ones in the first in these columns that I talked about. And you literally just have to count over. All right, so how are valence electrons involved in bonding? That's a really, really important question that you absolutely need to understand. Okay, so what we've got is, let's say we have 3 valence electrons. All right, so we're going to say that this guy has 3 valence electrons. I'm going to make them bigger. So 1, 2, 3. What's amazing about elements is that every single element wants its outermost energy level either full or have 0 valence electrons. So by full, it would have 8. By 0, it would lose all of them. So you're going to have to ask yourself, hey, how many would this want to gain to make 8? How many would it want to lose to make 0? In this case, it has 3 valence electrons. So in order to lose all of them, you'd have to lose 3, or you could gain 5. Because 3 plus 5 would make 8. Well, elements are exactly like people, and they're going to try to choose the easiest path. So which is easier, losing 3 or gaining 5? You only have to look at the number. So losing 3 would be the easiest. So these elements right here will always choose to lose those 3 electrons, because by losing those 3, we lose its outermost energy level, and there you go. Now, if we talk about another energy level, all right, or another one with, let's say, 6 valence electrons, so 1, 2, 3, 4, 5, 6, okay? If we had 6 valence electrons, that means that it could either gain 2 or lose 6. So which one is it going to want to choose? It's going to want to choose to gain 2. So if it gained 2 and we recounted, it would have had 8 in its outermost energy level. So this is exactly how they actually get charges. So if I were to do this for every single valence electron count, what I'm going to end up with are these wonderful charges. And I am going to want you to write the charges above. So this would choose to lose 1, so this would be a plus 1. This would be choose to lose 2 as opposed to gaining 6, so that would be a plus 2. These guys would choose to lose 3. 4 is a little goofy. It's going to choose to lose or gain 4, okay, because it can either gain 4 or lose 4. It's the same number, so it just depends on what it's bonded with to see which one it actually does. 5, it can either gain 3 to make 8 or lose all 5. So this is going to be the first time that they're going to choose to gain. So above this guy, you're going to write minus 3, and then you've got minus 2, minus 1, and 0. Now, why are these 0? Well, because they already have a full valence electron shell. So if this was my, instead of gaining 2, I already had those 2, such as this one right here, I already have the 8. It is perfectly happy. It will never choose to lose or gain any electrons. So what I want you to do is on your periodic table, above the valence electrons, I want you to write down the charges that each are going to have. And if you notice, it always goes 1, 2, 3, 4, and then it goes down 3, 2, 1. So it's kind of like going up a mountain and then down. So it goes plus 2, plus 3, and you're at your peak at plus or minus 4, and then now we're going down, so it's minus 3, minus 2, minus 1, 0. Okay? All right, hopefully you understand a little bit about valence electrons, a little bit about charges, what are periods, what are rows, what are columns, and how was it originally developed.